Okay, good afternoon everyone, and I'm happy to be presenting in Madeira finally after 2 years. And as you can see, it's a lot of emphasize some of them for you in an understandable way. This is a location. I come from Brno, Czech Republic. It's the physics of materials. My background is also connected to Oven in Austria, and we are at the we are interested in residual fatigue life of engineering components. So I'm going to talk about fatigue propagation. This is just one example. There are axles, but not limited to. It can be applied to many other problems. And so we are at the conference on fracture, so I deal with fatigue fracture. And classically we have the initiation and propagation phase. And actually the crack initiation phase is connected to short crack growth. And in both short and long crack growth, the threshold is the controlling parameter for the distribution curve. So that's why we think that the long crack threshold is a very important parameter, especially if we consider that most of the residual fatigue life lies in the near threshold regime. This is just to remind us that the applied load needs to be divided to the effective part and a corrective shielding part in case we have presence of cracks. So this is what I said, and fatigue crack growth rate is usually described using the stress intensity factor range, delta K, but we still don't have a reliable description of how to deal with the mean stress, so the load ratio effect. So one of the tools that is usually used is the fit by NASCRO, which takes into account plasticity in use crack closure. But actually the value of crack closure predicted by this scope is not always in agreement with what we find in reality. And we think that it is because it completely ignores the microstructure and the material side of the problem. So we have probably some missing mechanism or description which would depend on material. And in order to be able to say something about the differences between materials, we need to understand more the mechanisms. This was the part connected to plasticity use crack closure, but also we have the threshold regime. And in that case, we have other components of crack closure, and also we have some difficulties in measurement of threshold. So the second part of the talk will be focused on it. And if we talk about, especially in steels, if we measure the threshold value using different specimens, or even using the same specimen but in different laboratories, we can reach different values. And actually we found that oxide-induced crack closure is responsible for all this variation. So in our case, threshold is very important, and we want to know what are the influencing factors on this value. So we divide the threshold to the intrinsic part, to oxide-induced crack closure, and to other closure components. And the influencing factors, there can be specimen type, specimen thickness, or even width, humidity, loading frequency, loading history, we use the method for the measurement. And we also want to incorporate the knowledge to predict crack propagation and variable amplitude loading, because also due to oxide-induced crack closure, we have some load interaction effects. This is just to show the string yield model for plasticity-induced crack closure. We have the alpha parameter. This is the out-of-plane constraint factor, but also there is a parameter beta, which is the constraint factor in compression. And in the code, it is said that it is just 1, and we never actually study or deal with it how much this number would be. So our idea was that let's have a look at the parameter, if we can relate it to the missing mechanism. Because we have different plasticity induced crack closure effects in various materials, and here we have two steels, and we have the pre-growth rates here for load ratio 0.8, which is a non-closure ratio, and then we have data for 0.1, where crack closure was present. And we have delta K effective for the R 0.8, and we have K maximum for R 0.1. So the difference between these curves should be crack closure value. And we can see that we have for one of the steels marked by dark blue, we have quite small value of closure, and in case of the red steel, we have quite big difference. And this cannot be explained by the plasticity induced crack closure value by the available models. So if we just calculate from this data, the crack closure ratio should be in one steel should be 0.1, in the other one 0.5. But the models always predict something about 0.25 or 0.3. And it does have a very small dependence on material. So it depends only on monotonic properties. So you put the limit stress, the ultimate strength, and even if you vary them, you don't reach big differences between the closure ratio predicted by the models. And it does not depend on cyclic material behavior at all. Partly we are dealing with a finite element simulation of plasticity induced crack closure. You will hear about it in more detail by my colleague Radek Kubíček on Thursday, so please come to see his presentation. And he will talk about how the plasticity induced crack closure values can be different for different materials modeled by finite elements, and still just by monotonic properties. So there is some material model according to the stress strain curve. And the idea how to take into account cyclic material properties is by changing the constraint factor in compression beta that should be different from 1. And here's the idea. When you think about the plastic zone ahead of the crack tip, it has a certain size, and then we have fatigue loading and cyclic loading. So apart from the monotonic plastic zone, we have also the cyclic plastic zone. And plasticity induced crack closure is proportional to the size of the monotonic zone. But when we think about two different sizes of the cyclic plastic zone, this also has effect on plasticity induced crack closure. It has the opposite effect. If we have larger cyclic plastic zone, we have less plasticity induced crack closure. Because obviously in the monotonic plastic zone you stretch the material, and then there is a wedging effect in the crack wave. But if you have large cyclic plastic zone, you partially compensate the effect. So according to the behavior of the material, if it's cyclic softening or hardening, we have different ratio between the sizes of the monotonic and plastic zone. And this is what we can relate to the constraint factor of beta in compression. And also another idea is that the mechanism of fatigue crack propagation might not be fully given by the cyclic plastic deformation, planting resharpening mechanism, but also it can be partially given by microcracking. And this effect would also could be taken into account if we take different behavior according to the beta parameter, which is technically then not really a value of crack closure, but it's the same effect on the effective delta K that we obtain after taking it into account. So this is our idea how to take these effects into account, and we can then study differences between materials and between microstructures. Here's a few things that we should consider. If you are interested in any of the topics that I talked about today, so please come to me. I'd be happy to discuss any of them. There's not enough time. But just to show, I think most of you have seen this picture before. The problem is that if we have a specimen that is cracked, so at the edge we usually presume plane stress state. But the problem is that we model what is going on by two-dimensional model, assuming plane stress, and this is a different situation because in 3 dimensions we have a corner point singularity and the solution is different. So actually the plastic zone and all of the other things we study, especially for example, using the digital image correlation method, it's not actually correct. We should apply three-dimensional simulations. So here is an example from 3D finite element modeling. All of these plastic zones are from the 3D solution at different depths of the specimen. And the other one, this big blue, is from two-dimensional plane stress solution under the same loading. So you can see that really the shape and the size is different. Here's an example of threshold measurement, and it is for one type of steel, and we have dependence on air humidity. We have air humidity and measure threshold, and we can see that it kind of depends for larger humidity, we have larger threshold. It also depends on the rate of the load reduction, the delta K. For an example, for another steel, here again we have quite clear difference, dependence on air humidity, and if you can see, the variation is from 4 megapascal per meter to 7, so it's quite a big difference. And for residual fatigue life, it can mean several orders of magnitude difference. Here is what we mean when we talk about oxide-induced crack closure. Here this very dark brown marks the fracture surfaces were originated in the near threshold regime, so there was a low decreasing, and close to this line was the crack arrest at threshold. And as you can see, at large load ratios of 1.5 and 0.7, crack closure was limited because the crack was open, and we don't see anymore these marks of oxide. And then we can have a look at the fracture surfaces, and we can see this kind of typical structure for oxide particles. Also, there's a loading history effect. So, for example, if you apply the delta K decreasing method measurement of threshold, and you go down at this blue line, and after you measure the threshold and you want to go up again with the loading, you will not go at the same line. You will go to the red line, because here at very low crack growth rates, a large amount of oxide debris was produced at the fracture surfaces and increased oxide-induced crack closure. So then you need to apply larger delta K in order to repropagate the crack, and after you propagate out of the influencing area, you get back to the original curve. And also there is an influence of underload cycles, which means that if you apply cycles that are below threshold, they are non-damaging, and usually they are omitted in the residual fatigue-like computations, but they have influence because oxide debris that is produced during those cycles, and it has influence on the subsequent crack propagation, which will be slower. Here we have an example of how we can measure the thickness of the oxide debris with focused ion beam, and here we can observe different oxide debris thicknesses after application of different numbers of underload cycles. This is a cyclic R-curve measurement technique of cyclic compression tracking, and this is here just to say that each step of producing the curves, there are many cycles applied where oxide debris is produced. So actually in steels, the long crack threshold obtained by this method can be non-conservative. Let's skip this. And here is another example of when you make a K decreasing test. This is for this blue one, and again after reaching threshold, we don't get back on the same curve. An example for other different materials. So that's all I have to say, and I'll be happy to answer any questions. Any questions?
So what happens if crack closure is not correct? If the theory of crack closure is not correct? What happens with your result?
Yeah, it's one is plasticity-induced crack closure, one is oxide. In plasticity, there's much debate whether it's correct or not. What we know is there is a load ratio effect, and you may have a look at it. as a crack closure concept. Or you may have a look at it like, okay, we have delta K effective, which is smaller or larger, and we cannot be really sure whether crack closure is the mechanism causing this. So actually we may use the crack closure concept for describing the low ratio effect without being sure about the mechanism. If that satisfies your answer.
You mentioned about the influence of fatigue crack growth under small, generally regarded as non-damaging cycles. And I noticed that you'd fallen into the usual researchers' notation of showing blocks of fatigue damage with different stress rate, SIF ranges. But obviously in a real structure, everything goes crazy and you get smaller cycles in between larger cycles. Is that likely to have a significant impact, in your view, on real structures?
I think this is a question whether we have good quality of modeling of the effects of overload and underload regarding plasticity. There will be effect if we have some random, in time, the cycles, or if we have a block of small, block of large. There will be difference if we use different models, so that would be a problem. Regarding oxide-induced crack closure, we have a model where at each cycle, the oxide layer grows a little bit, but then the crack propagates away from it. So if we get correct crack growth rate, we have also correct influence of oxides. So this would be rather a problem of the plasticity-induced crack closure model.
Thank you.
In slide 14 or 15, you mentioned that you can see oxide particles on some yes, what load ratio was this tested?
This was 0.1 or -1. Because we had almost the same growth curves in terms of K maximum if we apply 0.1 or -1. And actually the growth of oxide really is caused by a large compressive stress just near the crack tip. And the fact that at -1 we have a compressive stress throughout the whole fracture surface is not significant. The stress is too small. Otherwise we would have the whole surface black, but we only have very close to the crack tip and near threshold region.